The acids and bases topic contains plenty of calculations and situations where you need to apply data, but it also contains a lot of definitions and facts that you need to be able to recall. This video is number 12 in a series of revision videos for physical chemistry, where you can practice recalling these key facts from your specification. If you look in the description below, then you'll find a link to a worksheet with all these questions so that you can go through them, answer them yourself, and then use this video to check your answers. Throughout A-level chemistry, you need to be familiar with 3 different definitions of an acid, depending on the situation we're talking about. The Arrhenius acid is the narrowest of these definitions, and although you wouldn't have called it this, this is the definition that you used throughout GCSE chemistry. So an Arrhenius acid is any compound which, when you dissolve it in water, releases hydrogen ions. Now, the Bronsted-Lowry acid definition is fairly similar in that it's a proton donor, and as we know, a proton and a hydrogen ion are functionally equivalent. They are the same thing. But the key difference here is twofold. Firstly, that this substance doesn't need to dissolve in order to be considered an acid, so it's entirely possible for you to have a gas that's an acid. And secondly, we're interested in the function, so we're interested in what the acid is doing right now. To make this a little bit clearer, you can think about the reaction of sulfuric acid with nitric acid. Now, both of those, according to the Arrhenius definition, are strong acids. They both dissolve in water and they dissociate to release hydrogen ions. But when we look at the reaction of the two of them together, we can see that it's the sulfuric acid which donates protons to the nitric acid. So here it's the sulfuric acid which is functioning as a Bronsted-Lowry acid, and actually the nitric acid, despite from an Arrhenius point of view being an acid, here it's actually functioning as a base. Then our Lewis definitions are even broader again, and you might not have encountered these yet if you've done your physical chemistry before your inorganic chemistry. But a Lewis acid is any electron pair acceptor. In the same way, we have 3 definitions for basic substances, and again these get more general as we go. So we start with the Arrhenius alkali, which again you would have met at GCSE, and this is any substance that can release hydroxide ions when they dissolve in water. And then we can become slightly broader than that and say that a Bronsted-Lowry base is anything that is a proton acceptor. Now, naturally, a hydroxide ion is always going to be able to accept protons, but also there are lots of other things that can accept protons. So, for instance, you could think about an ammonia molecule which can accept a proton to become an ammonium ion. Then we have our Lewis bases, which are broader again, and these are donors of electron pairs. Acid-base equilibria are established as protons are transferred between different chemical species. We use a logarithmic scale for pH due to the huge variation in concentration of hydrogen ions. So obviously for the pH scale to function, it's entirely normal for there to be variation in concentration of a factor of 10 to the power of 14. And so by using this logarithmic scale, we can avoid having to use standard form or just ridiculously tiny numbers. As you know, in order to express concentration, we use square brackets. So for pH, we're talking about the concentration of hydrogen ions, and we show that with square brackets around the ion. pH can be found by taking the negative log base 10 of hydrogen ion concentration. You'll sometimes find that people don't include the 10, it's just sort of implied, but I would encourage you to always include it in there so that you're recognising that the base of the logarithm is 10. Conventionally, in A-level chemistry, we always express pH to 2 decimal places. If we wanted to do the reverse operation and define hydrogen ion concentration in terms of pH, then we do 10 to the power of the negative pH. Kw, or the ionic product of water, can be found by multiplying together the concentration of hydrogen ions and hydroxide ions. As you can see, this is very similar to Kc, but without having the reactants on the bottom, so in this case it would be water. And the reason that the water is excluded is because it's effectively infinite, and because it's so much larger than the concentration of the hydrogen ions and the hydroxide ions, any variation in them just doesn't make a difference to the concentration of water, because the concentration of water is so much bigger. So it's effectively unchanging, and therefore there is no point in including it in the expression. Kw varies as a direct result of temperature changes. So Kw at 298 Kelvin is going to be different to Kw at 310 Kelvin. As we've just said, the value of Kw is going to vary with temperature. But the neutral point isn't defined based on the value of Kw or the particular number of hydrogen ions. It's defined as being the point where the concentration of hydrogen ions is equal to the concentration of hydroxide ions. And since both of those are going to fluctuate with temperature as water dissociates more or less, that's going to alter the pH because the concentration of hydrogen ions is going to change. Now, this next question isn't a pure factual recall question, and so maybe I shouldn't have included it, but these calculations are so fundamental to this topic, I thought it was worth putting one in. So we're given a value for Kw at a particular temperature, and we're trying to calculate the pH. Now, the first sneaky thing to point out is that in this instance, we've got barium hydroxide, and of course barium is in group 2, and therefore there are 2 hydroxide ions for every 1 barium ion. And so that means that although we've been given the concentration of the solution, that's not the same thing as the concentration of the hydroxide ions. So if the concentration of the solution is 0.1, that means that the concentration of the hydroxide ions will be 0.2. So now that we've established that, firstly, we need to define Kw. So we've said that's the concentration of hydrogen ions multiplied by the concentration of hydroxide ions. And that has a value given to us in the question as 1 times 10 to the minus 14. Now, since we know what the product of those two concentrations is, and we know what the concentration of the hydroxide ions is, we can rearrange this equation to find out what the concentration of hydrogen ions is. So I rearrange that equation, and that tells me that the concentration of hydrogen ions is 5 times 10 to the minus 14. And then to work out pH, I need to take the negative log base 10 of that hydrogen ion concentration, which gives me a value of 13.30. A hydroxonium or hydronium or oxonium ion is formed when a hydrogen ion joins together with a water molecule to make H3O+. And the reason we care is that actually in real life you're not really going to find hydrogen ions floating around on their own. They join up with water and stay in this compound form instead. A weak acid, as far as we're concerned for A-level chemistry, at least for AQA, is one that only slightly dissociates in aqueous solution. This is different to a dilute acid because when we talk about a dilute acid, what we're really interested in is the concentration of that acid in solution. So it's still possible for it to be strong, there just isn't very much of it there. Examples of weak acid include carbonic acid, citric acid, and also carboxylic acids like ethanoic acid. Ka is the acid dissociation constant, and when you write an expression for this, as with all of these constants, we want to have the products on the top and the reactants on the bottom, and because we're interested in concentration, we need square brackets. So you should have an expression that looks something like this. Now, the larger Ka is, the more of those products you have, the more hydrogen ions and the more anions, and this tells you that it's more dissociated, and therefore tells you that it's stronger. We don't write an expression of Ka for strong acids because they're basically completely dissociated. So you would just have a situation where Ka tended towards infinity because the top of the expression would be massive and the bottom of the expression would be virtually 0. Now, this next question is another one of these ones which isn't pure factual recall, but it's just a really, really common kind of calculation that you need to be familiar with. So we're given an expression of Ka for ethanoic acid and asked to calculate the pH. Now, the important thing is that we can only do this kind of calculation in this form for a weak acid in solution that's just dissolved. We haven't added anything else to it, and some of the steps that we're going to take here we wouldn't be able to do if we had added anything else to it. So this is not a buffer calculation, and it's really important that you understand that this kind of calculation is just for this weak acid that has dissolved in solution. So our first step is to write an expression for Ka. So the concentration of hydrogen ions multiplied by the concentration of anions divided by the concentration of the undissociated acid. Now, because there is no buffering and because there is nothing else being added, and only because there is nothing else being added, we can assume that the concentration of hydrogen ions and anions is the same as each other, because there isn't any source that has just given us hydrogen ions or just given us anions. They've come from the same place, so in each instance there will be an equivalent number of them. Based on that, we can take out the concentration of anions and put back in again the concentration of hydrogen ions. In other words, we can have hydrogen ions squared. I'm going to say it again, you can only do this because it's a weak acid dissolved in solution with nothing else added to it. You cannot do this for buffer calculations. So we can now rearrange that equation. We can multiply both sides by the concentration of the undissociated acid, Ha, and we can say that Ka times the concentration of Ha gives us hydrogen ion concentration squared. So if I actually did that calculation, I would get 8.5 times 10 to the minus 6, and that's my hydrogen ion concentration squared. So if I square root it, then I can get my hydrogen ion concentration on its own, and that gives me an answer of 2.92 times 10 to the minus 3. That's my hydrogen ion concentration, not my pH, so I need to do one further step where I take the negative log base 10, and that gives me an answer of 2.54. And of course, I need to report that answer to 2 decimal places because that is the convention for pH. We can also flip this calculation round a little bit and work out what the concentration of a solution is if we're given the pH. So firstly, I'm going to use the concentration of that pH to work out the concentration of the hydrogen ions, which in this instance would be 10 to the minus 3. Then I write that same expression for Ka that I had before. And again, in this situation, because we don't have any buffering, we don't have anything else being added, that means that I can take out the concentration of anions and just plug in hydrogen ions again. So I have this hydrogen ion squared term. Then I can rearrange my equation to tell me that the concentration of that initial acid will be the concentration of hydrogen ions squared, which I have because I got it from the pH, divided by Ka. So 10 to the minus 6 divided by 1.7 times 10 to the minus 5, and that gives me an answer of 0.059 moles per decimeter cubed. pKa is a measure of how strong an acid is. So the lower the number is, the stronger the acid is. And we can define pKa in kind of the same way that we define pH. So if you think about how you got from H to pH, you get from Ka to pKa in the same way. In other words, you take the negative log base 10. We can measure pH either using a chemical indicator like phenolphthalein or methyl orange, or by using a pH probe. A pH probe can be calibrated prior to use by using different buffers of known pH. So typically you'd have something like pH 4, pH 7, pH 9. So what you do is you submerge the probe in each one of those and take a reading, and then you plot a graph that we call a calibration curve. So we basically have a little scatter graph with the known pH on the x-axis and the measured pH on the y-axis, and you then draw your results onto this and draw a line of best fit through it and use this to adjust the results that you get when you're then using that pH probe. As part of this topic, you need to do titrations that involve weak acids and weak bases, but you should also already know how to do a simple acid-base titration from the earlier unit from the quantitative chemistry that you did back in year 12. So as with all of these required practicals, it's really important that you include as much detail as you possibly can, because these are level marked questions. So you're not going to get 6 marks for saying 6 true things. You're going to need to say more like 20 different things. So at each step, if there's equipment that you can name, you name it. If you can explain why you're doing a particular step, then you do that as well. So firstly, before you start your titration, you rinse your burette with the solution that you know the concentration of. So in other words, the solution that is going in the burette. So it's important that we rinse the burette before we start to remove any impurities, but we don't want to rinse it with water, because if we did, we would inevitably leave some water behind, and that would alter the concentration. Then, once we've rinsed it through really thoroughly, we need to fill up the burette and run the tap through to ensure that the air gap is full. If we didn't do this, then we would end up with inaccurate titers. So basically the first centimetre cubed or so that came out of the burette would be going into that air gap, and so you would end up thinking that you'd added more to the conical flask than you actually had. Then we take the solution that has the unknown concentration and we put that into a conical flask, and we obviously measure that out with a pipette. And the reason that we're using a conical flask is so that when we're swirling, we're not going to lose any of the solution because it's splashing out the side. So you measure out that solution using a volumetric pipette, which we use because it has very, very low uncertainty. And then we add a chemical indicator, and that is in there to identify the end point. And you place that conical flask onto a white tile in order to emphasize the colour change. Firstly, before you do your accurate titrations, you do a rough titration. So you quickly add the solution from the burette to the conical flask, and you continue to do this until you have the first permanent colour change. And then it's really important that you note what the volume is and actually write it down. So even at GCSE chemistry, that's a really common step for people to miss out. They talk about adding it until we have the first permanent colour change and then don't actually say anything about getting any data. So don't forget to do that. So once you've done that rough titration, you're going to do a couple of accurate titrations, and you repeat this, and then as you get near to the end point, you start adding your solution dropwise, so literally a drop at a time. And again, when you have your first permanent colour change, you note down the volume. As you're titrating, you swirl the conical flask in order to homogenise the mixture, and you use the wash bottle to rinse the burette and rinse the sides of the conical flask, and you're doing that to ensure that all of the solution that's coming out of the burette is actually going into your reaction mixture. And I should have included all of that on this slide as well, because I would include it in a written answer, but I was running out of space. Then you're going to repeat your titration until you have concordant data, and you should know that that concordant data is within 0.10 centimetres cubed of each other. We've already covered a few of these next questions within the last section, but anyway, the end point of a titration is that point where we see that permanent colour change. And if you've picked an appropriate indicator, then that should be at the same point as the equivalence point, which is where the solution becomes neutralised. But if you've picked an inappropriate indicator, they might not actually be at the same point. We don't rinse the burette with water because that would dilute the solution and therefore affect our concentration calculations. And we use that wash bottle to ensure that anything that comes out of the burette goes into the conical flask, and therefore we actually get an accurate titer for how much volume needs to be added before we see that colour change. The meniscus is that curved upper part of the surface of the liquid where you're measuring all your volumes from, and titers should always be reported to 2 decimal places, although that second decimal place will always be a 0 or a 5, depending on whether the meniscus is resting on the line or is directly between 2 lines. So you've now got 4 diagrams to draw, and for each one we're adding our base. So we're going to have volume of base added on the x-axis and the pH on the y-axis. So to start with, we're going to look at a strong acid and a strong base. And you're going to have this curve where we've got a vertical section in the middle, and then to the left and to the right of that you have slight diagonals. So they're not horizontal, they are slightly increasing as we go, but only a little bit. So initially we can add lots of base without the pH changing very much, and then as we reach the equivalence point, suddenly the pH rises very, very rapidly, and obviously pH 7 is going to be in the middle of that. And we would expect, because we're starting with a strong acid, to have a pH of maybe 1 or 2, and because we're adding a strong base, we're going to finish somewhere in the region of 11 or 12. Next, we've got a strong acid with a weak base. So we're starting from a similar point, starting from maybe a pH of 1, but the end pH is going to be lower because we're adding a weak base rather than a strong base. So you're going to have a fairly similar shape, but we're going to need to add more of that weak base because it's not going to be releasing so many hydrogen ions, it's not going to be neutralising the acid as quickly. And then we still reach that point where a single drop can lead to a big pH change, but that final pH is not going to be as high as it was with the strong base. Then if we look at a weak acid with a weak base, it's actually going to be quite a different curve. So we're going to do this on some different axes. So the first obvious change is that we're not going to start from pH 1 because this is a weak acid. So we're probably going to have a higher starting pH, maybe something like pH 3. And then the next thing you need to know is that it's not going to start with this very shallow diagonal that we had before, because actually we're going to have salt production initially, we're going to have buffering. So that first bit of base that's added is reacting with that acid to make a salt. So that first little kick is slightly different for a weak acid. Then we get that initial fairly flat, but it's a shallow diagonal happening. And then we get this upward kick. But unlike the strong acid that we had before, this is not going to be vertical. And it's also not going to be a very big pH change because we're looking at a weak acid and a weak base now. And then again at the top we're going to have this very shallow diagonal. Then finally we're going to look at a weak acid with a strong base. So again here we're starting from a slightly higher pH, so something like pH 3. And the initial part of the graph is going to look quite similar, although it might happen slightly more quickly. And then we are going to have that vertical kick where we have the equivalence point. and then similar at the top. The equivalence point is that neutral point where just enough base has been added to neutralise the acid, or just enough acid has been added to neutralise the base, depending on the titration you've done. The half neutralisation point on a titration curve is really important. It's the point where half of the acid has reacted, and the reason it's so important is because crucially at that point pKa is equal to pH, and so we can use this to help us to complete calculations. Initially, you only have the weak acid in solution because it's partially or slightly dissociated. And so that weak acid is going to very quickly react with the base to form a salt and basically to form a buffer solution. But as you carry on adding that base and the pH carries on rising, then eventually even a weak acid will fully dissociate to react with that base. A monoprotic acid is one which donates one proton or one hydrogen ion, whereas a diprotic acid can donate 2 protons. So your typical monoprotic acids would be things like hydrochloric acid or nitric acid, whereas a diprotic acid would be sulfuric acid. An indicator is a chemical that changes colour in response to changes in pH. When you're choosing an indicator, there are some things you need to bear in mind. One is that you want a really sharp colour change. In other words, you want something where if you add one more drop of acid or one more drop of alkali, you're going to see a colour change that is happening straight away and is very, very clear. The second thing is that you want a really distinct colour change. So phenolphthalein is a great indicator because it goes from being colourless to being hot pink, and there's just no way that you're going to mistake that or be confused about that. Whereas something that goes from yellowy orange to orangey yellow, you might miss that and you might just not be sure what's happening. A pH buffer is a solution that can resist a small change in pH when either a small amount of acid or a small amount of alkali is added to it. We form acidic buffers by taking weak acids and having them with their soluble salt, and this could either be by adding the soluble salt or it could just form as soon as you start adding a base to it, and then basic buffers are made from a weak base and their soluble salt. When a weak acid dissolves in water, this sets up an equilibrium between the undissociated acid on the left and then the hydrogen ions and the anions that it breaks apart to form on the right. When we add acid, what we're actually doing is adding more hydrogen ions. So Le Chatelier's principle tells us that the system is going to shift to counteract that change. The only way that hydrogen ions can be removed is by favouring the reverse reaction, and this will cause equilibrium to shift to the left. And so this means that more of the undissociated acid will be formed. If we have the same acidic buffer but add a base instead of an acid, then the hydrogen ions that are formed when the acid dissociates will react with the base to neutralise them. And this will then mean that the equilibrium then needs to shift to the right in order to replace those hydrogen ions, and more of the weak acid is going to dissociate. For any buffer, you should be able to work out what the pH of that buffer is when you first make it, and then how it will change as you add some acid or add some base. And you should expect the amount it changes by to be fairly minimal, because that is, of course, the point of a buffer. It's buffering pH change. So firstly, we've got just a buffer that we've made that nothing's been added to. And in order to calculate the pH, we're going to need to work out hydrogen ion concentration, and for that we need an expression for Ka. So Ka is the concentration of the hydrogen ions times the anions divided by the undissociated acid. Now, we start out and we can get the concentration of the anions from the concentration of the salt. So that's where those extra anions have come from. And then the concentration of the acid we've been given from the question, and likewise Ka we've been given from the question. We can rearrange that expression to get hydrogen ion concentration on its own, and then we can plug that value into a pH calculation to give us an initial pH of 3.62. Now, when we then start adding things to that buffer, what we need to consider is how is the system going to shift to counteract the change that we've made. So we're going to add some hydrogen ions because we're adding acid, and therefore the system is going to shift to remove those hydrogen ions. So firstly, we need to know how many hydrogen ions we've added. So I'm going to change my volume of acid to be in decimeters cubed so that I can then do a little calculation to work out how many moles I have added. Now for every 1 mole of acid that I add, so 1 mole of hydrogen ions, that will react with 1 mole of the anion to make 1 mole of the undissociated acid, because we're trying to get rid of those hydrogen ions, we don't want them in there, the system will shift to counteract the change. So if I'm adding 0.01 moles of hydrogen ions, then I will have 0.01 moles fewer of anions, and that will react together to make 0.01 moles of undissociated acid. So I can then adjust those numbers and put those into the same calculation that I was doing before, and that gives me a new pH of 3.55, and you can see that that's very close to the initial pH that I calculated, which is what I expect because it means that the buffer is doing its job. Finally, for the acids and bases topic, we have conjugates. So when we talk about a conjugate acid, we mean the species that is made after a Bronsted-Lowry base accepts a proton. So a really good example of this would be ammonia. Ammonia is NH3, and when it accepts a proton, it forms NH4+, the ammonium ion, and that is the conjugate acid. Another example we looked at right near the start, where you have sulfuric acid reacting with nitric acid. The sulfuric acid is functioning as a Bronsted-Lowry acid, the nitric acid is functioning as a Bronsted-Lowry base because it's gaining a proton, and so it's this positively charged ion that functions as the conjugate acid. Congratulations for making it to the end of this very long video, and if you do want some more help with those calculations, there are lots of videos on the channel. Look at the acids and bases playlist. If you did find this video useful, then don't forget to like and subscribe for more A-level chemistry coming soon.